Okay, so it is my pleasure to introduce our speaker, Mark Koo, today. Mark Koo is currently an assistant professor in University of Delaware. He received bachelor and master degrees from University of British Columbia in Canada and received PhD from MIT in 2015, all in physics. He then worked as a postdoc at Harvard. Mark has been working on near zero Kelvin technique to investigate the really low temperature quantum behavior. One of his recent researches is to develop the quantum sensing technology and to apply it to study quantum systems. His recent work on imaging the current flow of a graphene is one of few milestone works that clearly demonstrates the power of quantum sensors. So Mark, thank you very much for accepting the invitation, and please go ahead.
Yeah, thanks a lot. Can everyone hear me fine? Yeah, okay, great. Yeah, so first of all, thanks a lot for the invitation to give this talk. As has been mentioned, I was at MIT and also a postdoc at Harvard. So I was in the Cambridge area for quite a while. I don't think I ever stepped into the MERL, but I definitely have come by awfully close many times when I visited Moonland. So it's my great pleasure to finally get to meet you guys, even though it's online for this time. Yeah, and then so today I will. The aim of my talk is that I would like to give some introduction to the field of quantum sensing, specifically using the system of nitrogen vacancy or MV center endowment as an example. The talk could have gone very broad if I'm not careful, so I kind of try to be a little bit more focused. So I will be using MV as a specific system to demonstrate how quantum sensing can be done and how quantum sensing can be useful. And then I will also so that I will first give an introduction. Okay, what is quantum sensing, and why is it something that is a promising topic for people to work on? And then I will introduce MV quantum sensor, and then give some overview of how MV quantum sensing work. And I will pick a particular application, namely in the field of material science, which is my specialty. I will talk about a few of my works where we use a MV quantum sensor to obtain a new insight in condensed matter physics. And at last, I will provide some outlook. And I also want to say I meant for this talk to be also conversational. I understand the audience come from quite a diverse field and background. So if there's anything that someone want to pause me, just ask some question, or if I go too fast, please just pause me. Just unmute yourself. Let me know you have a question, and I will be happy to be interrupted. So I just want to let people know that you are free to do that. Okay, so let's see, where is okay, there we go. Okay, so first of all, what is quantum sensing? Obviously, when you talk about the various quantum technology, there can be lots of definitions that float around. I like to pick a couple of very nice review articles and use the definition from them. But first of all, I think it would be useful to talk about what is quantum technology. Here I draw the definition from this very nice review of the Quantum Technology Roadmap, a European community view. Here they define quantum technology as those that explicitly address individual quantum states and make use of the quote-unquote strange quantum properties such as superposition and entanglement. So then as a corollary, you can say, well, quantum sensor is basically a sensing that does just this. Here I draw another follow-up on that. Here I draw another definition from this a very nice review on quantum sensing by Deegan, Reinhardt, and Capellaro. I would say if you want to learn more about quantum sensing, this is a very nice review article. Here they define quantum sensing, describe the use of quantum system, quantum property, or a quantum phenomenon to perform a measurement of a physical quantity. And you might ask, well, so what kind of measurement could be done? So generally most of the application quantum sensing generally would measure electromagnetic field. Very often it might be magnetic field, which is also what I will talk about later, but it could also be electric field or electromagnetic wave or radiation in general. But temperature gravitational gradient and also pressure. These are actually all quantity that could have been measured and have been measured by various quantum sensor. And now, why is quantum sensing something that's of interest to people? Well, so it's actually starting to be quite widely recognized now that some of the most immediate quantum information science application will occur in the field of sensing. In this article, they also say communication, but I think it might be fair to say, well, I think a lot of people would actually even say that quantum sensing will probably have even more immediate application. And why is quantum sensing very promising? Is precisely the very fragility of quantum state is what makes them the basis of powerful sensing technology. So I will revisit this concept a little bit later in the next slide. Okay, now so once again, quantum computer is probably the most widely known application or envisioned application of quantum technology. So I think it might be useful to compare and contrast a quantum sensing versus a quantum computer, which is generally more well known. So requirement to build a quantum computer, well, the most basic requirement, as most people know, are these units called qubits, the quantum analog of the bits. In order to have qubits, you need to have a physical system with quantized resolved states. Generally, it means that you have two quantum states with a resolved energy level, and you can use them as qubit. You need to be able to control the qubit at will, which means that you need to be able to initialize the state. You need to be able to coherently manipulate each individual qubit, generally using external field. And this is what's needed for a single qubit gate. Clearly, you need to be able to read out the qubit state. One important ingredient is that you need a qubit to be able to talk to each other, or qubit-qubit coupling. And this is what enables you to have universal quantum gates. For example, if you want to have a CNOT gate, you have two qubits where the outcome of one qubit measurement is dependent on the other qubit. This means that obviously the two qubits need to be able to talk to each other. And lastly, a practical requirement is that the qubits need to be able to have their quantum state survive for long enough in order to operate for gate operation. The technical term here is that the coherent time needs to be long. And here, a coherent time means the time, the amount of time where the quantum state can be a well-defined quantum state can be maintained. Now, on the other hand, let's talk about quantum sensor. And actually, a lot of requirements are fairly similar. Once again, you want to have quantized resolvable states. So actually, generally, a system that could be used as a qubit for quantum computer could also be used for quantum sensor very often. So you also want to have a qubit for a quantum sensor with the quantized resolvable states. And once again, you want to be able to initialize the state, manipulate the state, and read out the state. Now, one major difference for quantum sensor from quantum computer is that instead of the qubit coupling to each other, you want the qubit to couple to the quantity to be measured. Because obviously, if you want to sense a quantity, you want the qubit to be able to be affected by this quantity. And lastly, you do also want to generally have a sufficiently long coherent time instead of for gate operation. This is for the qubit to interrogate the external quantity. So the external quantity can lead to sufficient perturbation so that the qubit is have some effect. Okay, then now let me further discuss why is quantum sensing a useful field, a nice field to work on, and specifically why, if you don't want to work on, like why, for example, okay, instead of working on quantum computer, why might one want to work on quantum sensing? So here, let me first discuss some major challenges that we face for building a quantum computer. So qubit for quantum computer require the following. First, as I mentioned, qubit need to be able to talk to each other. And in particular, you do want the qubit-qubit coupling to be strong. At the same time, as I mentioned, you also want the qubit to live long enough. Or the technical term is that we want to have minimize the decoherence. Decoherence referring to the quantum state being scrambled by the environment. So in other words, we want the qubit to minimally couple to the environment. But then you realize these are, practically speaking, generally fundamentally conflicting requirement. It is because if a qubit couple weakly to something else, it means that it's going to be so let's say if a qubit coupled weakly to the environment, it also generally means that it's going to couple weakly to each other. Generally, the idea is that the larger the qubit, the stronger the coupling. An example will be superconducting qubits. They have very strong qubit-qubit coupling, but they also have a fairly, generally a low, not as a long coherent time. Where, for example, for MV center, which I will talk about, they're much smaller qubits, so they are actually minimally coupled to the noise environment. So they have very long coherent time. But at the same time, it is very difficult to couple MV to each other. So that's why people generally don't, at least mostly have not been trying to use MV to build quantum computer. But on the other hand, with quantum sensor, you don't have these kind of fundamentally conflicting requirement. First of all, as I already mentioned, qubits generally are sensitive to perturbation. But if you can, if you are able to come up with engineer a system where without the external signal you want to mention, the environment is very free of noise. So for example, let's say if you want to measure magnetic field, if you can engineer a system where the native magnetic noise is very little, then the qubit itself will have a long coherent time. But then once you have the external signal you want to interrogate, then the qubit will be perturbed by that. So if the qubit is sensitive to a particular perturbation, and if you can minimize the decoherence due to the natural environment, then it means that you can have highly sensitive sensor, because then you have a qubit that has very long coherence time on its own without external signal. But once you have the external signal, it is easily perturbed by the external signal. So then you can have a very sensitive detection. Now, on the other hand, another reason why a quantum sensor is receiving a lot of attention is because, let's say, if you want to push sensing into smaller and smaller scale, it also means that your sensor needs to be smaller and smaller. And at some point, as we all know, once the system is small enough, eventually it has to be described by quantum mechanics. So in other words, let's say even if you don't want to do quantum sensor specifically, but if you just simply want to measure on a small scale, like say nanometers, like a nanoscale, you need to have a small sensor, which invariably has to be described by quantum mechanics anyway. So here, so basically you end up with a quantum sensor anyway, if you want to measure on a very small scale. And lastly, quantum sensor, very often they rely on behavior that are tied to a fundamental constant. So for example, with MV sensor, the degree of freedom that we're interested in is the spin, which coupled to magnetic field. And spin is a fundamental, and here the how the spin is affected by the magnetic field is given by the electron gyromagnetic ratio. So in other words, how much the external signal is going to perturb MV is tied to fundamental constant, which means that you don't need to calibrate each individual MV sensor, because once you have an MV, you know how, like, what is the degree at which its energy is going to be shifted. So it means that you can have a high degree of accuracy, repeatability, and precision. And very often you don't have to calibrate each sensor one by one. So as a result of these considerations, quantum sensing enable highly sensitive detection at a small scale. They're expected to have immediate application, primarily because they're technically significantly easier to implement compared to quantum computing. It's also a highly multidisciplinary and rapidly emerging field, which I will allude to in a moment. Okay. So now, having given a fairly broad introduction to quantum sensing in general, here I will zooming into a particular system, namely a nitrogen vacancy center. So now let me first talk about what is an MV center. As I mentioned, MV center reside in diamond. So when I mention the word diamond, perhaps the first thing you might think about is carbon atoms arranged in tetrahedral lattice. Now, an MV center is a particular defect in which you have a carbon replaced with a nitrogen atom. So that's also known as a substitutional nitrogen. And it's paired out with a neighboring missing site or vacancy. So namely, the carbon atoms missing there. So you have a nitrogen, substitutional nitrogen, a vacancy. So that's why this object is called an MV center. It turns out that MV center is what's called a deep level defect in the wide bandgap semiconductor. A deep level defect referring to that it's the electronic state live within the bandgap, and therefore the states, instead of being delocalized, the electronic state is localized. So what it means is basically what you have is you basically have something that's like an atom, artificial atom residing in the crystal lattice created via material engineering. And it turns out that the electronic the electronic spin associated with MV center provide a qubit, and that can be used as a platform for quantum technology. As I mentioned earlier, it is very difficult to couple MVs to each other. So that is also why people have not been making a lot of attempt to make a quantum computer out of MV yet, though there are some efforts that are around. But on the other hand, MV, they do serve as an excellent sensor of magnetic field. And in particular, they can achieve high sensitivity and also high spatial resolution. So let me describe a bit more of the key properties of MV center, just to give an idea of how it works. As I mentioned, MV can be considered as an atom-like object. So it has a ground state, and it also has a bunch of excited states. And the ground state can be excited using laser light. Generally, what people use is that they use 532 nanometer or a green laser light to excite the MV. This is actually this will actually excite the MV into some higher excited state because the lowest excited state, the energy between the lowest excited state to the ground state is actually in the red wavelength, about 650 nanometer. But just because green laser light generally is much more readily available in terms of higher power, so people just simply use 532 nanometer. They excite the MV, and then the MV will decay through the excited state and gradually and eventually back into a ground state, emitting a photoluminescence in the range of 650 to 800 nanometers. So basically in the red wavelength. And then in general, we particularly were interested in the ground state property. So the ground state has a spin, and it turns out the spin number is 1. And which means if you revisit the basic quantum mechanics, it means that it has 3 magnetic sublevel, which we'll label using the MS quantum number. The magnetic sublevel can have the MS quantum number of 0 or plus and minus 1. It turns out that at 0 magnetic field, the plus and minus 1 are degenerate, so they have the same energy, but are separated from the 0 state by about 2.87 gigahertz. That's also known as the zero field splitting, and that's just simply a result of the spin-spin interaction of the interaction of the electron that hosts that electronic state that form the MV. But one key property of MV is that in the presence of the magnetic field, the plus and minus 1 level are split by the Zeeman energy. The zero level does not have any magnetic moment, so the energy just remains at 0. But the plus and minus 1, they have a opposite magnetic moment. So therefore, their energy is shifted up for the plus 1 or shifted down for the minus 1. And it is this change in the energy level due to the magnetic field that's provide the basis for MV to be able to measure the magnetic field. Okay, so now let's revisit the requirement for quantum sensor. So as you can see, we do have a quantized state, and then the state coupled to the quantity to be measured, namely magnetic field. Now, one requirement that we need is the qubit initialization. And it turns out that for the MV, you can realize it using optical excitation. It turns out, and I will not go into detail, but it turns out that if you excite the MV with a green laser light on the order of, let's say, a microsecond, then all the MV will be optically pumped into the MS equals 0 level. Okay, let me also just bring up the laser pointer. Okay, so all the MV will be pumped or initialize into the MS equals 0 level if you excite the MV with a laser for long enough. The MV state can also be read out via the photoluminescence emitted when you excite the MV. And it turns out that the MV is brighter when it's in the MS equals 0 state compared to in the plus or minus 1 state. So basically, we can just shine the light. We can measure the amount of photon emitted by the MV. And by looking at how much photon is emitted, we can tell which state is the MV in. The MV can be coherently manipulated using microwave. So let's say if you initialize the MV, so they're initially at 0 level, you can use a microwave that is unresonant with the transition between 0 to +1, for example, to bring the MV into the +1 level and back. You can also do the same with a 0 to -1 transition, once again, by using microwave at the appropriate frequency that's unresonant with the transition. So you can select either the MS to a -1 or MS to +1 transition, and then once you have selected, for example, a pair of state, like say 0 to -1, using your microwave frequency, then now you have defined your two-level system. And this two-level system will serve as your qubit. And lastly, MV has a very long coherence time. It's on the order of millisecond at room temperature. This, in fact, is basically the longest coherent time for a solid state base qubit at room temperature. So this is also a reason why MV is a very versatile quantum sensor, because you can actually use it even at room temperature. So that's a pretty nice. Okay, let's see. So here, let me just show a couple pictures of MV sensors in action. Here's a piece of diamond containing a high density of MV, and here I'm shining a laser light through it. And you can see that there are red fluorescent emitted by the MV within the diamond. In fact, if you have a dense enough MV ensemble, you can also see the red fluorescent just by putting a note card in the path of the MV fluorescent. For example, you can see here, there's this red spot that is the fluorescent emitted by the MVs. Or if you have the MV that are sparse enough, you can also see them as an individual isolated emitter, such as in this high resolution of fluorescent scan. Okay, so a question one might have is, how do you create these MVs? There are several ways. Here, let me just mention the two ways that people generally will create MVs. First one is by implantation, and this is generally useful if you want to create a single MV or low density ensemble, or if you want the MV to be very close to the surface. So to do this, one would start with a high purity diamond created via chemical vapor deposition, and then you will implant energetic nitrogen. So the nitrogen would then penetrate into the diamond and leave a wake of vacancy, a trail of vacancy as that nitrogen goes in. Now you do need the vacancy to pair out the nitrogen to form an MV. So the way you do that is that you can anneal the diamond at about 800 degrees Celsius. At this temperature, the nitrogen does not move, but the vacancies are mobile. But once the MV are paired, the MV is stable at this temperature. And this leads to a conversion efficiency of about 5%, meaning roughly out of 20 nitrogen you implant, one MV will form. You can control the density and energy of the nitrogen, and to control the corresponding density of MV, and also the depth of the MV. The depth of the MV typically range from a few nanometer to hundreds of nanometer, depending on the energy of implantation. Now, another way to create MV is by incorporating nitrogen during the growth process. And this is generally suitable if you want to create a high density ensemble, if you want the MV throughout the entire diamond, or have MV confined within a micron thick layer, for example. So in order to do this, then you would basically incorporate nitrogen right within the CVD synthesis of the diamond. And then the resulting diamond generally will have a very high nitrogen content, but yet not much MV. So generally the diamond might look brownish, and then you would irradiate with the electron and the anneal, which will create vacancy and then facilitate the formation of MV. And then the resulting diamond would look purplish. That is also the color of a diamond when you have a lot of MV centers. And just to give you a sense of what an apparatus looks like, here's an apparatus in my lab. So we use MV to probe condensed matter systems. So generally we will have some device of interest, and we have a diamond containing MV that is on top of the device. And then we will have an objective that collects light. So then a physical picture you can see is here. Here you have an objective, and here you have a sample, and the diamond that's sit on top of it that's being illuminated using green light. And then here's an optical setup. And this pretty much is the the optics part of the MV. So it's pretty compact. There are also laser and also microwave generator and also computer that's not part of this picture. But the main point is that the setup does not need to be large. In fact, there are also commercial apparatus as well. Here is a quantum diamond microscope that is manufactured by the company QDM-IO. And you can see that this is basically like just a stand on top of optics a breadboard. And then here, or you can see from this picture here, the actual apparatus is really just this large compared to this monitor. There are also a scanning probe microscope using MV that are commercially available, such as made by QZaver. And you can see, yeah, the setup is not too large. The main point is that the setup is actually not that large. And generally, if you're just looking at a room temperature application, the setup can really just occupy the space of a desk. Now, you might ask, okay, so what are some useful, how is MV quantum sensing useful? What are some of the applications? So here I briefly overview some of the sensing application with MV that people are either already using or are developing. So well, my field is condensed matter and material science. So obviously that's an application I'm familiar with, and I will be talking about some result that we have accomplished using MV quantum sensing to study condensed matter physics. Now, another actually fairly interesting application of MV is the study of geoscience, and in particular, there are these rocks that are magnetic, and the people are interested in figuring, like looking at the magnetic distribution of the rock. And this is actually, this particular effort is actually not completely new. Like people have already been using squid to study the magnetization in rocks, but using MV Center is a relatively newer application. And this is nice because this allows you to have a high resolution imaging of the magnetization within rocks. And in fact, these two applications, condensed matter and geoscience, are the applications that are already producing a result. And what I mean by that is that people are no longer just doing the proof of principle demonstration, but people are actually using MV to produce some useful result in this field. Another very interesting and fairly recent development is using MV for the diagnosis of the integrated chips. The idea is that, okay, let's say you get your integrated chips, and then you are told, okay, that it does something. But then how do you actually know? Like maybe when you're like operating it, but it's doing something nefarious without you knowing it. And then, but then you don't really want to open it, because once you open it, you might perturb its operation. So then one want to have some non-invasive way to be able to diagnose what is happening in the IC. For example, whether there might be some Trojan that's built in. And then a way to do a non-invasive diagnosis is that, well, we know electrical current generally magnetic field. And a magnetic field is generally a hardly screened. And that is also a basis for NMR because magnetic field is hardly screened. So then if you can measure the magnetic field or map out the magnetic field of the IC without opening it, it can provide a way to diagnose what's happening within the IC. And that is an effort that's been going on starting recently by a couple groups now. Biosensing is a big topic that's being investigated in the MV, and there are many different specific application people are looking into. Here, let me just mention one thing that people are very excited about and are working on. And the idea is to detect the magnetic field generated by the neuron activity. And once again, let's say, just imagine, okay, you want to figure out what's happening inside your brain. And then and obviously, like, okay, one way to do it is by poking some probe or some needle into your brain. But clearly, like most people don't want to avoid that if possible. But then once again, neuron activity, whenever you have a current that's flowing around in general magnetic field, and then which you could in principle measure. And then if you can measure that outside of the brain, that provides a non-invasive way to diagnose what's going on. So what people have done as a proof of principle is that they're able to detect the magnetic field generated by the neuron activity inside a worm. And in fact, the worm was still alive and intact when they did this measurement. So basically, they put a worm on top of a diamond, and they were able to measure the magnetic field generated by the worm. And of course, like this is so far just a proof of principle demonstration, but it does demonstrate the promise of this approach to figure out for neuroscience. Using MV for nuclear magnetic resonance is another very active and very active topic, which also promise a lot of impact. The main idea is that people have shown that you can use MV to detect nuclear spin on a very small scale. For example, in this picture, you can see that people have done NMR or MRI of the fluorine nuclear spin on the micron scale. Here's another work where people detected the NMR signal from a micron size volume of a nuclear spin. And basically this accomplishment enable ones to be able to look at perform NMR on a very small scale, and has a lot of very important application both in chemistry and biology. Yeah, there's a question, Matt.
Yeah, so how does the spatial specificity work here? Is the diamond very tiny, or is it placed in extreme proximity to what's being sensed?
Right.
Or is
so
it directional?
Proximity is key. One might think about, okay, one way you might here generally people do NMR by having a piece of a slab of diamond, and then you will have maybe like say some solution that's on top of a diamond or flowing across a diamond. So let me see if I can draw. So basically you have a piece of diamond, and then you have some solution on top, and then you have the MV that are very close to a surface. And having MV close to a surface is key because each MV generally interrogate a volume that is approximately given by its distance with respect to the sample. And then in order to have and in order to actually get the spatial information, then generally what you would do is that you would collect the MV fluorescent using a camera. Here, the nice thing is that because the fluorescence encodes the information of the signal from the MV, and then you can use a camera to capture a large area of view. So that allows you to have the basically the spatial information. That's basically how this work here is done. They use a camera to capture the signal from the MV, and therefore able to map out the nuclear spin distribution.
So this is wavelength limited.
Yes.
In terms of the fluorescence.
Right. Yes. If you're doing a measurement this way, now you can also people have also demonstrated you can actually use a magnetic gradient to do a MRI, just similar to what a conventional MRI does, where instead of basically you're using a magnetic gradient to encode the information in Fourier space, and then you would then obtain the signal in Fourier space, and then perform the inverse Fourier transform to obtain the signal in real space. And then it turns out that because people can generate sufficiently strong enough of a gradient, so in principle, spatial resolution on the order of tens of nanometer is actually possible. So that's so if you want to go into a smaller resolution, there's also this Fourier gradient technique that's possible. And you can also do a super resolution optical measurement as well. There are also optical super resolution measurement that people have demonstrated with MV.
Neat.
Okay. All right. Okay. So let me continue. But also, now all these applications I just mentioned here are kind of, you might say more like at least so far mostly academic, but they're also very practical application that the industry are actually pursuing. For example, GPS-free navigation. The idea is that, let's say, for example, you have a submarine, and you want the submarine to don't have to always come to the surface to receive a GPS signal. How do you navigate? Well, one idea is that if you can map out the magnetic field of the ocean bed in advance, and then and if you can do it with sufficient precision and accuracy, then your submarine can remain submerged and then and it can navigate itself by looking at the magnetic field signal. So that is one application in the navigation area. Another application is that people are looking into our gyroscope to measure the rotation. So here, basically, MV is also sensitive to rotation. And then people are interested to develop very sensitive and also calibration-free gyroscope using MV. Okay, so let's see. So I think I will spend a few minutes to go through talk briefly about how MV quantum sensing work, and then I will then talk about also quickly go through the work that I've done. Let's see. So here, let me just talk about the simplest MV sensing scheme, which is optically detected magnetic resonance. So here, the idea is that you apply a laser and microwave continuously, and then you monitor the fluorescence while you sweep the microwave frequency. So, so let me just give you an example how this works. So let's say initially you have the microwave that's far detuned from the transition. And then because you are continuously applying the laser, so your MV is always in the MS equals 0 state. So you have high level of fluorescence. And then, but as you sweep the frequency, once you hit the resonance, then you start to bring the MV into the -1 state, for example. So then now you have a dip in the fluorescence because the -1 state has a lower fluorescence. And then as you continue to sweep the microwave frequency, when you once again you get another dip when you're at the 0 to +1 transition. So here now you see there are two resonances, each one correspond to the 0 to -1 and 0 to +1 transition. And then by looking at how far these transitions are split, and also knowing the geromagnetic ratio of the MV, we can figure out what is the magnetic field, in this case 100 Gauss in this measurement. So this is a simplest measurement possible. But there are also pulse MV measurement where you truly actively manipulate and manipulate the MV quantum state. Generally, this will involve you first use a laser to initialize the MV into the MS equals 0 level. And then you will use a combination of a microwave sequence to manipulate the MV spin. And then and also use that for interrogation. And at last, you have a readout. You apply a laser again to excite the MV and also collect the photon for readout. So let's see. So let me just use an example of a Ramsey interferometry measurement as an example to demonstrate these kind of a pulse measurement. Okay, and to talk about this, I will use the block sphere and also block vector picture. The idea is that for a two-level system, you can represent the state as a vector pointing along a sphere, where the North Pole is usually considered as the one of the two-level state, and the South Pole is the other two-level state. And so let's see. Okay, I forgot to label something. So, and here we're going to use the North Pole to represent the 0 state, and then South Pole to represent the +1 state, assuming that we have picked the 0 to +1 transition as our two-level system. So what happened with a Ramsey measurement is that you use a laser to initialize your MV spin into the North Pole, namely the MS equals 0 level. And then you use a microwave to rotate the block vector into the equator. Here, specifically, we're bringing the block vector into the equator, pointing along the sigma x direction. And this specifically is the superposition of a 0 +1 state. And then what happened here now is if there is a magnetic field present, sorry, let me see. Okay, there we go. If there's a magnetic field present, then the block vector will start to precess. In other words, it will collect a phase. And one can also write it out in this the state representation this way. Basically, the +1 state will start to obtain a phase in its complex prefactor. And the more the phase that it occur, the higher the magnetic field is, assuming that you let it interrogate at a fixed free precision time tau. So at last, in order to measure the magnetic field, we want to measure what this phase angle is. So the question is, how do you do that? If you just simply apply another green laser light to read out the MV state, one thing I should also mention is that the readout basically measure the projection along the sigma z axis. So then if you just measure the projection along the sigma z, you see that it's always going to be 0 if you just read out at this moment. So the way we do that is that we perform quantum tomography where we apply one more microwave pulse, which will basically measure either the projection along the sigma x axis or the projection along the sigma y axis. So in this case, for example, if we apply a microwave pulse to rotate along the sigma y, this basically will allow us to measure the projection along the sigma y axis. And then, so now when you perform a projection measurement along the sigma z, basically you will get a signal that looks like this, where you will have a signal that modulates depending on your phase angle, and that goes either as a cosine or sine, depending on depending on what kind of rotation that you perform. And you can imagine that if you, for example, if you perform a rotation along both x and also y in 2 separate measurements, this will allow you to perform an unambiguous measurement of the quantum state after the free precession. And let's see, okay, yeah. And so, yeah, this basically provide a way to measure the magnetic field. And here, this Ramsey interferometry measurement is just one example of the pulse measurement that actively manipulate the quantum state. And there are more examples, which I will not go into detail here. Okay, so now let me use the remaining time to discuss. Sorry, let me clear up the annotation here. Okay, there we go. Okay, now let me use the remaining time to talk about the application condensed matter system. Okay, so one question is, okay, why is it interesting to use the magnetic sensing, such as with MV Center, to probe material science? Well, a reason is because very often interesting phenomena in material will either manifest as a spatially varying current or a magnetization. Just as an example, one phenomenon that people are that's on the forefront of condensed matter science is so-called quantum anomalous Hall effect, where you have these topologically protected dissipationless current that flows along the edge of a magnetization. And people are very interested in this phenomena because you have these topologically protected dissipationless current, which means that you can possibly use them as low power consumption electronic. And furthermore, because the edge current is defined by magnetization, and there are ways to rewrite magnetization. And then so this allows you to have a way to reconfigure these dissipationless current. So that's why people are very interested in this quantum anomalous Hall effect phenomenon. And now you see this phenomenon has both magnetization, magnetic domain, and also spatially varying current. So in fact, this kind of phenomena provides a ripe ground for magnetic study with magnetic microscopy. So yeah, as I mentioned, the idea is that both magnetization and also electrical current generate magnetic field. So if we can perform microscopy of magnetic field, that provides you a way to peek into what current and magnetization is doing on a microscopic scale. And as people very commonly say, seeing is believing. If you can really visualize what the current and magnetization is doing, that provides you a very powerful way to understand what's going on in the system. Okay, so let's see. Let me also just mention that there are multiple measurement tools that perform some kind of magnetic microscopy. MV is not the only one, and in fact, MV has its particular set of advantage that make it very suitable for some scenario. Well, for some other scenario, you might want to use some other technique. I will not go through this discussion in detail here, but if someone is interested in a comparison and discussion of some of the leading magnetic microscopy technique, I will point you to this recent review paper, which provide a very nice in-depth comparison. But now let me just go straight into a case study of using MV to probe condensed matter system. And this is using MV to probe hydrodynamic electron fluid in graphene. So what do I mean by a hydrodynamic electron fluid? So let's first think about what, let's say, what happened in a conventional copper wire, let's say a copper wire in your electrical system at home. In a conventional metal, what happened is that you have a lot of scattering that will relax the momentum of your charge carrier. This could be impurity or these could be phonon, but the main idea is that your charge carrier is frequently has this momentum scramble as it try to move in the presence of the electrical bias. So if you apply a constant uniform electrical bias, the current density will be uniform. And here, a picture I like to use is that imagine you have a pipe that's filled with sand and you pour water over the sand. So the gravity is pulling the water down, but the water is not just going straight down. It's like scattering. Each water molecule is scattering across the sand. So then basically the water molecule kind of diffuse through the sand. And that's also basically more or less the picture of what goes on with a conventional conductor. But let's say if you can suppress these momentum relaxing scattering, for example, by reducing the impurity level and also somehow suppress the phonon, then at some point, electron scattering start to be important. And these electron scattering, they preserve momentum. So then you actually get into a regime where the charge carrier have a collective movement. And as a result, they develop viscosity. And so now here, the analogous picture is that now in the same pipe, you remove the sand, and then now you just have water that just flow through the pipe. And as you may recall, if you have a pipe flow, the flow is actually, profile is actually not uniform. Sorry, let's see, there's something in the chat. But it's not a question. Okay, yeah, so once again, if anyone has a question, please just raise your hand or just unmute yourself and let me know if you have a question. Okay, so going back to hydrodynamic flow, so in the present, where if you have a flow, if you have an electrical system where the dominant scattering is the electron-electron collision, then the analogous picture is that now you have water that's just flowing through a pipe, and as you may recall, a pipe flow actually has a non-uniform current profile because of viscosity. Let's see. Why does the electron, the question is, why does the electron velocity go to zero at the pipe surface? That is a very good question. And yes, whether you actually have a parabolic flow does depend on the boundary condition. So here I'm assuming a particular boundary condition that's called a no-slip boundary condition, basically meaning that the velocity is forced to be zero. And some of the there are various scenarios where why the velocity might be forced to be zero. One could be that the boundary is rough. In fact, people have done a study where they basically they are able to change the boundary condition by making the surface rougher. But yes, the assumption of the boundary condition is not a trivial one. For now, I'm just going to assume that in general we have a no-slip boundary condition. But I will also say yes, in general that's not necessary. Cannot necessarily be assumed. But at least in the study that we mentioned, we do have a no-slip boundary condition, which means the velocity is forced to be zero. Okay, all right. So let's see. Let me continue. Now, electron hydrodynamics has been received a lot of attention in the past couple of years, partly because it provides a description of transport of interacting system, which is a very difficult problem. And also there are some interesting potential application for electron hydrodynamics. Now, one question is that how do we visualize the electron fluid? For a classical fluid, like say liquid or gas, very often you can just use the camera to take a picture and to look and see the flow pattern. But do we have an analogous camera for charge flow? Well, as you might already guess, the idea is that we could map out the magnetic field generated by the current density. And then it turns out that in the case of the 2D current, there's one-to-one correspondence between the magnetic field map and the current density. So once we map out the magnetic field, then we can construct the current density. Here in this work, we use two different measurement modality. One is wide field imaging, where we have a diamond containing an ensemble of MV near the surface, and we construct graphene device on top of the diamond. And we use the camera to image the fluorescence from the MV. This allows us to map a 2D large area at the expense of the spatial resolution. where our resolution will be limited by the optical diffraction, and then where we also use the scanning probe microscopy, where we use the diamond tip containing an MV to scan across the graphene device. In this case, we can achieve a higher resolution at the expense of longer measurement. So for this measurement, we don't do a 2D scan, we do a 1D scan. Okay, so let me summarize the result. So from wide field imaging, this is electrical current distribution. Here we source the current from the top and we drain on the bottom left. You can see that the electrical current distribution we obtain follows the expectation, what's expected. And in particular, if we look at the line cut, if we look at the line cut, so here's the data. And if we compare to a uniform distribution with a diffraction limit, we see that our data clearly does not match that, where our data matches very well a viscous, diffraction limited viscous profile. So that's good. And then in order to obtain a high resolution measurement, we now move on to a scanning probe microscopy. So here we have a channel and we send the current along the Y direction and we scan along the X direction. As a control measurement, we first perform the measurement on an ohmic metal, a palladium, and here you see that we obtain a current that is basically nearly uniform along the width of the channel. Here, the width of channel is W, and it's in agreement with the ideal uniform flow within 5% error bar. We also perform measurement on the disorder graphene device, where disorder is intentionally introduced. And once again, we have a nearly uniform profile. And but where now then when we measure clean graphene is made clean by a boron nitride encapsulation, we get instead a very nice parabolic shape that matches very well to ideal viscous flow. One immediate question you might have is what is this dip here? Let me just say that we were not clear what's the effect at the time, and there had been numerous theoretical investigation that follows since. Right now, one of the best explanations is that this has to do with the electron hole recombination, because our system here is actually an electron hole system where the graphene the chart near the charge neutrality point. But let me also say that this dip is fairly robust. We have measured across a couple different devices, and the dips is always there. The dips actually is also can also be tuned somehow, where if we start to make the graphene a little bit more disorder, the dips start to be disappear. So that's also something interesting, which is also consistent with the electron hole recombination scenario. But the main point I just want to mention is just that the measurement is the feature that we obtain here are real and repeatable. So the main summary here is that we provide the observation of the viscous transport in electron fluid, and we can observe the transition from the ohmic in a disordered graphene to hydrodynamic flow in a clean graphene. And this provides the first direct visualization of the viscous charge flow. And let's see, I think I would like to wrap up. I'll just say very quickly, at UD, our group has also performed a measurement of the room temperature 2D magnetic system, a 2D magnet, where these are material that are just like graphene. You can exfoliate to be very thin layer, and then they're also magnetic. And one of the challenge with these material is that most of them are not magnetic at room temperature. But at the same time, it is difficult to characterize them as a thin flakes, because at a thin flake, they lack magnetic signal to be probed by a conventional tool. So at UD, we collaborated with growers who grow these material, and we by using a MV diamond to image the straight magnetic field of these thin flakes, we can confirm that when exfoliated, these 2D magnetic material, they remain magnetic at room temperature and above, and we can image the straight field generated by these thin flakes, verify that they are indeed magnetic. Okay, and I can go back and discuss this more if there's time and if there's an interest. But I do want to take just maybe 2 minutes just to quickly give some outlook. And once again, this is basic. And in general, I would say all of the area that are actually being investigated are worthwhile, like are certainly interesting, or otherwise like people would not be looking at that. But specifically with condensed matter and geoscience, people have already demonstrated that you can use MV to produce a useful and new result. So it's definitely worthwhile to continue for the community to continue to work on this area to produce new result in this direction. In the rest of the development, in the rest of these areas, such as IC diagnosis, biosensing, and NMR, there are some ways to go, but they're definitely a high impact result if they're successful. And certainly the industry is also interested in developing a practical tool for navigation purpose. So that is also an active area and useful area to investigate. And also there is both a need and also already development to commercialize some of these technology. For example, quantum diamond microscope and also MV scanning probe microscope are some of the commercializable apparatus. And I would say, yeah, there is definitely room and also need to continue to further produce these kind of apparatus, taking into account of the need of the community. And let me also just mention, there are a number of companies that are around that are basically developing MV-based technology. And here, let me just, I just mentioned a couple of names. Some of them are established company and some of them are a startup. I do want to mention, perhaps for the interest of this audience here, some of the potential problem that might be of interest to the audience. One is the inverse problem, where, as I mentioned, with MV, you primarily detect magnetic field, but then ultimately we're interested in the underlying current distribution or magnetization. So how to go from magnetic field to, say, for example, current is called an inverse problem. And it's turned out to be quite a fairly non-trivial problem. And in particular, the inverse problem only have a unique solution in the case of strictly two-dimensional current. Once you go beyond that, there's no unique solution exists. But still, it is very possible that you might still obtain useful information about the current distribution. Now, an inverse problem is particularly important for Trojan detection in integrated chips, because very often your IC might have several different layers where activity happens. So then this will be an example where the inverse problem is not unique, but you might still be able to obtain some useful information if you are clever. One possible solution will be to use machine learning. So then you can go from the magnetic field that you measure to the activity that's actually happening within the IC. And it's already being investigated by some of the references, some of the work I reference here. And also more generally, the inverse problem is quite widely applicable, not just with MV, because there are also other magnetometer as well. So I think this might be a useful, potentially interesting topic for the audience to consider. And at last, let me just also, I also just want to acknowledge the people I've worked with. The work at Harvard is done in the group of Ronald Walsworth and Amir Yacobi. And I want to acknowledge my student and postdoc and my collaborator and also my funding source. And thank you very much for your attention. And very happy to, very much welcome a question and comments.